All right, so okay, this is gonna be easy then. I need a quick show of hands, like who has used Elasticsearch or OpenSearch or Solr before? Cool. What about Vespa, or at least heard of it? Okay, cool. Right, because that's kind of my background. I've been working for more than a decade with the Lucene search engines, and I joined Vespa like 1 year ago. So today I want to give you an overview of the Vespa architecture, because I find it really interesting, and hopefully you'll find it too. If you end up using Vespa or not, I think that's a cool kind of different way, different approach of doing things, certainly different than Elasticsearch does it. And I'll use Elasticsearch as a reference point just because it's more familiar to me, but I was assuming that it will be also more familiar to you. Okay, so it's going to, I'm going to have two sections, basically. One where I actually go over the architecture on 4 points. One, how do we scale the data layer? How do we scale the stateless layer? How do we scale distributing the configuration, so how all of this is going to be in sync? And then, of course, monitoring and logging. And then the other thing that I'll show how you'd run Vespa in Kubernetes, and I'll do a quick demo of that and show how that might change in the future. So hopefully that will add a new layer to kind of revisit the architecture topics that I'll be covering until then. Okay, so just to make sure we're all on the same page, because especially nowadays terminology is kind of confusing, search engine, vector DB, retrieval engine. The problem that we're trying to solve here is as old as it can be. It's information retrieval, right? So we have a bunch of data, and what we want to do is to take a chunk of it and get the top n results ranked by something, and or some breakdown of that chunk that we just filtered, right? So examples could be in e-commerce, right? I want the most relevant phones, and I also want a breakdown of those phones by manufacturer, price, whatever. Could be a recommendation system, could be I'm a data scientist and I want to see what's in this corpus. I don't know what is in it, so I want to slice and dice it. And all of this has to happen in real time, right? So I want the response in milliseconds or maybe seconds. I don't want to wait an hour or a day. So this is the problem space, and there are lots of tools that can do with this. Lucene search engines, talk about Vespa, but of course there are lots others that I'm not necessarily familiar with, but they come from different angles, like pure vector DBs that add filtering capabilities on top, and other tools. So I won't talk too much about it because I don't know what to say. Okay, so let's kind of take the architecture, and then I'm going to go over each topic in more detail. So we have a stateful data layer, right? We have some data that we probably need to scale across multiple nodes. Then there's also some stateless processing. So when queries come in, when documents come in, then we need to do some stateless processing. That has to be scaled often as well. Then we have a config layer, which distributes the configuration to all these nodes so that they're in sync. And then we have to take care of metrics and logs, right? So I'll take each one at a time. I'll show you how Elasticsearch does it, and then how Vespa does it. Okay, so stateless workloads. Let me give you an example. So, or a few examples rather. We have some documents coming in. We may want to create embeddings, right, to do vector search. That is stateless processing. We have a query coming in. We have to distribute that query to all the nodes holding data and then get the partial results, merge them into a final result to the client. That is also stateless processing. For results, right, we get the results. We may want to forward them to an LLM and then do retrieval augmented generation that way. That is also stateless processing. With Vespa, for example, that LLM could be local, so that, again, is significant load if you also host the LLM yourself. So Elasticsearch does this with node roles. So if you use Elasticsearch, you maybe know, like you can have data nodes, and then you can have, let's say, coordinator nodes that don't hold data, but they're like all the nodes. They're just configured to do specific tasks. Vespa has a different approach in the sense that we have services, which are separate processes. So for this, we call this the confusingly named Java stateless container, which is not a Linux container. But it's a Java process, and it's separate from other services that do other things, which can be native processes. For example, the content node, which actually holds the data, that is a native process. I want to take a quick detour and explain the confusing terminology and why it's called container, for example, and you'll probably find some other things as well also in the architectures, because Vespa has a really long history. That predates at least when Docker and Kubernetes became popular. So you'll see some overlap, for example, with Kubernetes functionality. It's not like they reinvented the wheel, it's just the wheel wasn't there, or it was square. One thing that I want to highlight here is this bit where it was more than 10 years ago that Vespa added support for tensors, which you can use for vector search, but you can also use it for other things. Anyway, back to the main flow. How do we distribute the configuration? And here I want to clarify what I mean. I'm referring to metadata, everything that is not a document or a query, everything that either tells the cluster how to function, so the behavior definition, how it should react to your input, things like schema, things like which model to use when generating embeddings. And the other part is the data distribution, right? So what's the state of the cluster? Which node is up? Which bit of data is where? And Elasticsearch treats this as a whole. So every node, I mean, this whole metadata in Elasticsearch is called cluster state, and every node in the cluster has a copy of the cluster state. But only one node is allowed to write to this cluster state, and that is the active master or cluster manager. And as you may imagine, this can become a bottleneck, like if you have a very dynamic cluster with lots of cluster state changes. In Vespa, this is treated separately. So the behavior definition goes into what we call an application package. And an application package is simply a collection of files which contain things like schema, which node should be where, and how much heap it should have. Everything that is configuration goes into this set of files, and we say that we deploy this application package to config servers. So these are like another service, another standalone process. We deploy the application package to the config servers. They store those files in Zookeeper, which is typically embedded, but it doesn't have to be. And then every other node in the cluster will have another process called the config proxy. So the config proxy syncs up, at least by default, it may not, syncs up with the config server, fetches the configuration, and says, okay, you're supposed to do this. Data distribution is handled by two other services. So we have cluster controllers, which elect themselves a leader, and the leader will check what we call the cluster state, which is which nodes are up and which are down and which are in maintenance mode and things like that. And that cluster state is served by distributors. So every node holding data will have a distributor process, again, separate process, and they will say, okay, this bit of data belongs to me or to some other node. And one other thing is that in Vespa, it's deterministic. Like if you know how many nodes you have and your replication factor and things like that, you basically know, because there's an ideal bucket distribution algorithm, you know where each bit of data is. So you don't have to sync that up really, like who really holds which chunk of data. And here I want to talk a bit more about the data distribution, because I assume you may be more familiar with how Elasticsearch or Solar OpenSearch does it, or maybe how Kafka does it, where your data can be sharded, right? So you can piece it up into multiple shards, and then those shards can have a bunch of replicas. And then what happens is, when you add a new node, some of these shards can migrate to the new node, and then you're scaling out. And the important bit here is, before and after, you need your total number of shards in that index. Ideally, it should divide by the number of nodes. Otherwise, you may have hotspots. And the other thing is, when those shards are moving, they're not really moving. What happens is we create a new copy, and when that copy is done, that's when we remove another replica. And this is an interesting trade-off here, because on the upside, we copy the actual files. We copy the indexed files on disk, and we don't have to index them again. The downside is, while we're doing this, the primary shard keeps accumulating on the transaction log. So it's a bit of a race between how fast we can copy the data and how much the transaction log accumulates. Which in practice means you can't have shards that are too large. The rule of thumb is 50 gigabytes, but of course it depends on the hardware and network and stuff like that. In Vespa, it's a completely different approach, which you might have seen with things like Cassandra or Redis, where documents are divided in virtual buckets. So they're not actually different files on disk. In fact, nodes have, data structures are per node, not per shard or per segment like they are in Lucene. And this enables Vespa to be really fast when it comes to queries. So we've done a benchmark with Elasticsearch, and Vespa is roughly 1 order of magnitude more efficient when it comes to queries. And then when you scale, you can basically move documents corresponding to these buckets. I mean, you don't do that. This happens automatically to the new node. So this is much more granular, and so you don't have to think about shards. There's really not a problem of hotspots. But of course, there's no free lunch. The trade-off is that because document structures are per node, you basically have to reindex the documents themselves to the new node. So moving the data is more expensive than it is with Elasticsearch or Sol or Lucene, where you move the shard itself. Okay. Moving on to monitoring. So Elasticsearch and friends all have metrics APIs. You can connect to them, get the metrics for the whole cluster or for the local node. If you get them for the whole cluster, this will be more taxing, of course. And it uses a thread pool that also does other things. For example, responding to pings from the master node. So there might be the cluster stability might be affected by your metrics or the other way around. With Vespa, this is yet another service. It's called the metrics proxy, and it exposes metrics in Prometheus format as well. With logs, the Lucene search engines use log4j. This is very straightforward. In a Kubernetes setup, you just log to standard output. Everything is fine. Vespa has a more old school approach, again, kind of blaming that on the history, where there is a common logging module, but they all log to files, and then there's a logd service, which rotates the files and forwards them to an admin server, which runs a log server, kind of centralizing all the logs. And this, of course, can be changed in the future, because we have all the specialized logging tools nowadays. Speaking of that, I'd like to show you a bit of how Vespa runs in Kubernetes. So this is the high-level view of the cluster. We have the stateless so-called container nodes, and then we have content nodes holding the data, and then we have the config nodes that handle the configuration, the application package, and the log server effectively. And to deploy Vespa on Kubernetes, you would have to have two steps. You don't just start it up. You have to first bootstrap it, and by that I mean you need to start the config servers, and there's basically one image to rule them all. So you run that image and you just say config server, and it's going to start the config servers there. And the others will just start up, but because we don't have an application package yet, they will not really start the services. So only when we deploy the application package to the config servers, that's when there's a process called config sentinel that lives on every node, pulls the config, and says, okay, I'm supposed to be a content node, or I'm supposed to be a container node. And all that is defined in the application package in a file called services.xml. So services.xml says, okay, which process needs to be on which host. So this is kind of mirrors what Kubernetes does and kind of traces back to the history of like pre-Kubernetes. So this has to be, at the moment, synced up with, let's say, your stateful set definition. So if you say you have 3 nodes in the stateful set, then you also have to have 3 nodes in services.xml. And then everything will be fine. And I'll actually show that live. By the way, I will have at the end, there's going to be a QR code with the link to these slides, which have all the links to everything, like, for example, the GitHub link to the demo. There's a sample apps repository, so if you want to explore Vespa and for different use cases, you can have a look at those sample apps. There's everything from running it on Kubernetes to doing all sorts of fun stuff with regarding relevancy. Anyway, so what I have here is, let's say, a demo script. I've already done part of it, so I've created a kind cluster, and I've created a Vespa namespace where everything will happen, and I've started the config servers. So if I look here, the config servers are there already ready. So I'm just going to port forward one of them, and then I'm going to check for their health. Right? So this says it's up, so we're fine, which means we're ready to start everything else. Yeah, so this will start pods with all the other services. And I'm going to show the YAML files in a second. Okay, so while this is starting, the config server is what I showed earlier in the slide. So it has these config server argument, but other than that, it has the same image as, let's say, a container node, which also uses that, but only says services. So if you look at the definition of the pod, like for container, at least the gist of it right here is the same as it is with the content node, which holds data. But what we actually want is for them to be very, very different. They would run different processes. So for that, let's see if they actually manage to start. I'm going to do a port forward for the container service, which lives on 8080. That's kind of the default port for it. So let's see. Nope, they're not ready just yet. Oh, they're not ready because I didn't put the application package. My bad. Let me put the application package. So I'm here, and I'll say Vespa deploy, and then I'll show you the application packages. Okay, DNS warning. We can ignore that for now. So the application package. What I really care about is a hosts file, which includes like DNS names of my pods, and then I can give them an alias to reference them more easily. And then the services XML that I mentioned earlier, which basically takes these aliases and says, okay, I'm going to co-locate some of the services we've been talking about. So in config server 1, 0, 1, and 2, so these are basically the aliases to my config pods. This is where config servers should live. This is where cluster controllers should also live. Of course, I don't have to co-locate them, but in this case, I do. There's also another service that I didn't mention so far, which is called Service Location Broker. It's for container nodes to know where to write data. This is, again, a part where we can totally replace this with a Kubernetes service and get rid of this process altogether. And then container nodes live on container hosts, and content nodes live on content hosts. And then let's say I'm using this for music metadata, so I'm pointing this to a schema called music, where I have a bunch of fields. So all this is in the application package, and when I say Vespa deploy, this goes there. And now, let's try again with the port forward and the health. And now my container nodes are up. So the application package was deployed, and now I should have the nodes as I configured them to be, which also means that I can show you how you insert a document and run a query. So this would Hello. Would this select still work if it's collapsed? I guess we'll see. There you go. So this will put a document, let's say one Coldplay album here, and we can also query. Let's say I'm going to search for Dreams in the album name. By the way, this is real time, so which is different than Elasticsearch and a lot. So there's no concept of a soft commit. When we write a document, as soon as we get the acknowledgement, the document is searchable. And so yeah, here I'm searching for Dreams in the album field, and it should get my document back. So that was it. Right. Where can this go in the future? Of course, we can have specialized images. So for each service, we could have one container image, and then we don't need this whole shebang of syncing up what's in Kubernetes with what's in the application package. I'm told that removing the config sentinel, which kind of does this syncing up, is not as trivial as I think, but we'll see. An easier lift is to decouple logging, so we can simply log to standard output and let the specialized tools with it. The metrics proxy doesn't have to, and I think this applies to Elasticsearch as well, like doesn't have to aggregate if Prometheus can do that kind of work. And then that service location broker, I think, can go away if we can use a service here that looks at the content nodes, and we'll use that service. So that's what I have prepared. If you have any, so this is a QR code for these slides, and you have all those links to all the resources, and yeah, feel free to reach out to us, to me, or ask questions now, because I think we have some time, right?
Yep, thank you, Radu.
Welcome. Hey.
The slide will be on, so if you want to grab a screenshot, take a QR code. I'm always wary of taking random QR codes. I'm always wary of taking screenshots of random QR codes. You never know where they're going to take me.
Yeah, this is a very nasty virus that goes to Google Docs and will wipe your phone.
But yeah, we've got questions.
Yeah, questions.
I'll get.
Yeah, thank you. So you mentioned at some point about sharding, that when adding a new shard, you need to reindex the data in that shard, right? Or
let me go back there, and I think we can talk. So you mean here?
Yeah.
Yeah. So when you add a new node,
Okay.
the actual documents have to be migrated to that node. You don't migrate the underlying files there. So when you index documents, right, you have some data structures on disk, like inverted index, like what have you. So those, you can't just move them around because they're per node. So you effectively reindex the documents. So if you have, like I have here, I have 3 nodes, and then each node has a third of the data, then I basically have to take a quarter of the data of each of nodes 1, 2, and 3 and put it in the new one.
And who decides what are the key slots distribution of the data? Is it like you, or you the programmer, or the system? Like the key slot, because I would assume like when you add a new shard, this is a shard, right?
No, this is not a shard. Like these are nodes, and the little bits here are called buckets, but these are like virtual buckets, and you have like, I think 2,000 of them by default. So you don't really decide. Like this is just done automatically. Like it's like a routing key, if you will. But it's virtual. Like these buckets are not separate files on disk. It's just Vespa knows that document 1 belongs to bucket 1 and document 15 belongs to bucket 3.
Okay, but how does it know? Like based on
it's like a hash function, I think.
Okay, so it's a hash function. And what do you mean by you need to migrate your data?
Oh, sorry, then it was, I said it wrongly. You don't need to. Vespa does it automatically. But you just need to be aware that this happens. Like if you add a new node, it's not like the data is going to be there. It's like it's going to take some time to migrate and reach a stable state again. But in that time, it's all perfectly usable, right? Like it can still serve queries and such. And new documents belonging to those buckets will go directly there because they know they have to be routed to the new node.
And how does the system know where to reroute the queries? So let's say you add a new node.
Yes.
And how does it know, because you're in the transition process, right? So
Yes.
the documents are being copied from node 3 to node 4, let's say. How does it know not to redirect to node 3 if the file was not?
This is where these distributors are aware of where each bucket is currently located. And if it's kind of coming up or down, like all the states, the cluster controller pulls it, so it knows if nodes are up and down and everything, and then the distributors will know.
And who is notifying the distributors?
The cluster controller is notifying the distributors.
So the cluster controller sort of monitors the buckets, and then it
monitors the nodes.
The distributor. And how do they reach consensus, all the distributors, or is the cluster controller
Cluster controllers elect a leader, so only the leader will do that. If the leader goes down, another one will be elected.
So the leader of the cluster controller
Yes.
group. Mm-hmm. Nice. Thank you.
You're welcome.
Cool. Great discussion. Yep.
Hello.
Oh.
Sorry, maybe you have already explained this.
No
So
worries.
it's a search engine. How does it compare to using just Elasticsearch?
Well, I think the trade-off is that it's kind of a more complex system, but it's faster when it comes to queries, especially when it comes to vector search. So if you want like a benchmark, there's on this last slide, there's this benchmark that you can look, there's like an 82-page. But the gist of it is that, especially if you're looking at vector search, or especially if you have multiple vectors per document, it's like the more complex the query, pretty much, it's the better bang per buck you're getting with Vespa. It's kind of more complex to set up, especially if you have like a smaller setup. It's slower at outright writes. So the initial feed is going to be slower in Vespa, but updates are faster, like true updates are faster because we don't have to reindex every document. So that's the gist of it.
Okay, thank you.
You're welcome. Any other questions?
I guess not. But you're still here.
I'll be around.
Are you going for drinks later as well?
Yes.
So you can chat over a drink as well. Thank you. Big round of applause for Radu.